In order to understand the quantum mechanical model of the atom, we need to understand how light waves move through space, and how to label those waves. The top of a wave is called a crest, and the bottom of the wave is called a trough. The distance between two crests or two troughs is called a wavelength, and the height of that wave is called amplitude. The speed of light in a vacuum is 3.0 times 10 to the 8th meters per second, and that is for every light wave possible. Now you'll notice in this diagram here that as we move from radio to gamma rays, the wavelength becomes significantly shorter. Hence, if you look at the visible spectrum, you'll see that red light and purple light obviously have different size wavelengths. Red has the longest wavelength, purple has the shortest wavelength. This is called the electromagnetic spectrum, and you notice most of these. You know radio. Microwave is what we cook our food in. Infrared is heat. Visible is what humans can see. Ultraviolet gives us suntan. X-ray is what helps us see broken bones. And gamma ray is what we saw in the last section with radioactive decay. Something you need to know is that as the amount of energy in a photon increases, the frequency increases and the wavelength decreases. Here we see that the radio wave has a long wavelength, meaning it has a low frequency and also a low energy. Gamma rays, on the other hand, have a very short wavelength, meaning they have a very high frequency and very high energy. So remember this, that as energy increases, its frequency will also increase and its wavelength will decrease. Hence the reason why red light, having a longer wavelength, has a lower frequency and a lower energy than purple light. One of the main discoveries that helped us develop the quantum mechanical model was the photoelectric effect. This says that electrons are emitted from metals when they absorb energy from light. If you look at this metal of potassium here, you'll notice it's hit with 3 different wavelengths of light. Remember that red has a longer wavelength and lower frequency than the purple that's on the right side. When we hit the metal with the red light, no electrons were emitted. It didn't have enough energy to emit electrons. And as we hit the metal with green light, electrons were emitted. And purple light, electrons were emitted still. Max Planck used this idea to come up with this formula at the top, E equals hv. The hv represents a packet of energy that was given off by the metal. He called this packet of energy a quantum, and it represents the amount of energy that's able to be emitted or absorbed by electrons using photons. There are 3 main types of spectra you should know. The first one's a continuous spectrum. This is a spectrum that contains or appears to contain all wavelengths of light, but not spectrum lines over a wide portion of its range. If you look at this spectrum below, it looks like all wavelengths of light are represented, hence a continuous spectrum. Contrast that with these 2 types of spectra. In the top one, we call this an emission spectrum or a bright line spectrum. Notice the hydrogen, mercury, and neon do not give off continuous spectrums when they are heated. They give off only certain wavelengths of light. You should also notice that they're different from each other, and it helps scientists determine what elements are being burned in a fire. The spectrum down below is what we call an absorption spectrum. It's the opposite of a bright line spectrum. We have a continuous spectrum, and the hydrogen is blocking out certain wavelengths of light. Notice the bands in the absorption spectrum for hydrogen line up exactly with the bright line spectrum of hydrogen. Niels Bohr took the idea of Planck and theorized about the atom. He said that electrons are found in shells. When an electron is found at its lowest energy level state, it's called the ground state. And when that electron gains energy, it jumps up to an excited state. That electron is not stable in that excited state and will fall back down into its ground state. As it does so, it will release energy in the form of hv. The h represents Planck's constant, 6.6 times 10 to the negative 34th, and the v represents frequency. After Bohr came up with that atom, somebody came up with the wave-particle duality theory. It stated that all objects behave as particles and can have a wave-like pattern. Those with less mass have higher and more measurable crest. Essentially, particles can move in waves, but sometimes act as particles and not as waves, giving us the dual nature of light. So now scientists thought that electrons are found in shells, but they move in a wave-like pattern. The last theory that helped us develop the quantum mechanical model was Heisenberg's uncertainty principle. He stated that one cannot tell the exact location and momentum of an electron. You see, on the right we have an electron, a yellow electron. On the left we have a photon. And the only way we can see the location of an electron is to hit it with that photon. But as you see, as we hit the electron, it takes it off its original course. So we might know where its location was, but we have no idea where it's going next.